Okay, it's time to start. So our next speaker is Temple He from Caltech, and his talk is about connecting shockwaves and memory. Please.
Thank you very much, Laura, for the introduction. I would like to begin by thanking the organizers for putting together this wonderful conference and for giving me the opportunity to present. So today I will be talking about this pair of papers that I wrote with Anna Maria Recleru, who is currently at King's College London, and Catherine Zurich, who is at Caltech. And this pair of paper, it focuses on the infrared sector of gravitational theories. Now, there's a parallel set of development in the context of gauge theories that also a lot of parallel conclusions are drawn. And this was done in these papers with Prahar Mitra, who is currently at Amsterdam, as well as with Catherine and Alex Ramakrishnan, who is also at Caltech. So if you're interested in seeing the analog of the gravitational side of the results I'm going to present, I refer you to these three subsequent works. Okay, so let's start from the very beginning. So over the last decade or so, Strominger and collaborators have discovered that there's an amazing equivalence in the infrared sector of gauge theories and gravity. Now, what this means is that there are the three corners of this triangle, which is now called the infrared triangle. These three corners are separate fields that have been studied in the context of gravity that I will be talking about today for over half a century. And now we are starting to appreciate that they are in fact the same phenomenon, except expressed in quite different languages. So just to quickly give you a very brief schematic, what we understand now, for instance, is that the word identity associated to the asymptotic symmetries is precisely the soft theorem. And similarly, you can also think of the soft theorem as being the Fourier transform of the memory effect. So let's just delve a little bit into the history of this. So let's just start in chronological order. So in 1962, Bondi, Metzner, Vandenberg, and Sachs, they were studying the set of transformations that preserve the boundary fall-off conditions in asymptotically flat spacetimes. Now, originally, they expected to recover the Poincare group, but what they discovered was something far richer, and this is now called the BMS group after the founders. So for instance, what a class set of transformations that consists of BMS group are the super translations. And these are essentially angle-dependent translations of the celestial sphere. So here we have a Penrose diagram. I took this from Andy's lecture notes. So this blue circle here, this corresponds to the celestial sphere. And you have these angle-dependent translations, and these form the super translations. And these preserve the boundary fall-off conditions and are symmetries of the S matrix. Now, a couple of years later, completely independently, Weinberg was studying scattering amplitudes. And what he discovered was the leading soft graviton theorem. What does that mean? A soft theorem is precisely the following statement. So here I'm just going to talk about the leading soft theorem. But basically, suppose you have a scattering amplitude involving n+1 particles, one of which is a graviton. And now you take the graviton, which I label here with this wiggly line, you take its momentum to be soft. Miraculously, what happens is that you can write this amplitude as the original endpoint scattering amplitude without this soft graviton, multiplying a universal constant. Another way of saying this is that if you take the momentum of the external graviton to be small or soft, it causes the scattering amplitude to factorize. Now, finally, we have the memory effect, which was first discovered by Zeldovich and Ponerov in 1974. So these were astrophysicists. And perhaps the easiest way to think of the memory effect is suppose you have two objects, and they have some fixed spatial separation between them, let's say stars or black holes. Now, you pass some gravitational wave or gravitational radiation between the two objects. Now, while the gravitational wave is passing, you expect their separation to fluctuate. And after the gravitational wave has passed, you expect their separation to be fixed once more. Nevertheless, the separation between the objects before the waves passing and after the waves passing is different. And in that sense, gravity retains a memory of the gravitational waves passing. So this is exciting because the permanent change in the separation between the two objects is potentially measurable. And this allows us to initiate a contact between our theory and experiment. It allows us to essentially put this infrared triangle and put it on to experimental, essentially to make connections to experiments. This is certainly something that we would expect to see once LISA is launched. So today I will be focusing on this memory effect. And in particular, I want to connect the memory effect to shockwaves. And the way that I'm going to do this is I'm going to try to obtain a gauge invariant on-shell action that describes both classes of metrics. And I will be very concrete in what I mean by the class of metrics that describe the memory effect and the class of metrics that are shockwaves. Now, once we obtain this on-shell action, you may wonder, well, what is this good for? And I will hopefully proceed to convince you that this is actually equivalent to 3 different objects that has already been studied quite extensively in the infrared literature in gravity. Namely, it is going to be precisely equivalent to a particular class of supertranslation charge. Supertranslation charge, they're typically parameterized by a function f. I will show you exactly what form f has to take in order for this on-shell action to be equivalent to this. And supertranslation charge, of course, is precisely the charge that generates these supertranslations. This is something that Ash, Dakar, Hansen already appreciated in the 70s and 80s and was recently brought into prominence again by Barnack and Truchot back in 2009. Furthermore, it will be equivalent to something perhaps a little bit less well known, but also is fairly well established now, the soft effective action, which was first introduced in this lovely paper by Kapets and Mitra back in 2021. And finally, the last thing I will demonstrate is that this is equivalent to the shockwave effective action. This was first written down by the Verlinde back in 1991 in an effort to produce the correct equation of motions for shockwaves, but more recently it was used by Verlinde and Zurek to study metric fluctuations. So this is a goal, and I just want to pause to see if there are any questions moving forward. Okay, if not, so let's begin. Okay, so first I have to say, what do I mean by asymptotically flat spacetimes? So in particular, I will adopt the Bondi gauge, and I will use what are called flat null coordinates, because these coordinates are particularly easy for us to do computations. Essentially, what they do is they flatten the celestial sphere into a plane. Now, let me break this down a bit. So here, I have written the asymptotically flat metrics in Bondi gauge. And the first line here, this is precisely Minkowski spacetime with no corrections. So z and z bar are simply parameterizing the coordinates, complex coordinates on the celestial 2 sphere. R is roughly speaking a radial coordinate. So when I take R goes to infinity, it goes to scry plus. What's nice about this coordinate system is they also simultaneously parameterize scry minus as well if I take R goes to minus infinity. So in effect, it captures both scry plus and scry minus in one coordinate system. And finally, U is roughly speaking the retarded null direction. So what it does is once I am either on scry plus or scry minus, it parameterizes the direction along scry. Now, what about these other 2 lines here? These 2 lines are simply subleading corrections to Minkowski spacetime. They are subleading because as you go to large R, these are all, these either vanish. So for instance, the UU component of this vanishes, and so I reduce back to Minkowski, or they are subleading because in the transverse components, this, the dz squared term, it goes as R, but it's subleading with respect to R squared. So MB is a Bondi mass aspect in some sense. So what it does is parameterizes the longitudinal fluctuations. And CZZ is typically called the shear tensor. It's parameterizing these transverse fluctuations. Now the dots, these are simply components of the metric that are completely determined once I impose the vacuum Einstein's equations. Furthermore, the Bondi mass aspect and CZZ, these are not mutually is a constraint equation that relates them, which again follows from the Einstein's equations. So in particular, you see that the change in the body mass is precisely given by the derivatives of what I call NZZ here, where NZZ is just the U derivative of CZZ, and this is the News tensor. So with this, the body mass aspect and the shear, I can now fully determine the solution to the vacuum Einstein's equations, and so these constitute the asymptotic data of my spacetime. Now, I'm going to restrict to a particular class of these asymptotically flat metrics, which we call memory metrics, because they are going to be a special case where it completely isolates the leading memory effect. So the profile is the following, which is it's given by a step function, and it's less than U0. I have just this minus 2 dz squared c term. And so this is simply a Goldstone mode that's parameterizing the vacuum degeneracy of the asymptotically flat spacetime. Furthermore, I have the this end mode, which turns on after U is greater than U0. And this is precisely what essentially it causes this memory effect, because it causes a shift in the shear. And so the memory at N, so this you can oftentimes think of it as a emission of soft gravitons, but because it's also parameterizing the memory effect, we will also use the term memory mode. So we will use the term soft mode and memory mode interchangeably. Now, what we want to do is we want to parameterize this, also characterize this in terms of shock waves. So the memory effect, as I said, is a DC shift due to the passing of gravitational waves. And one way that you can think of this, as was introduced by Straminger and Jaboda back in 2014, is that this is due to a vacuum transition, due to a supertranslation. And so what we would like to think of the soft shock wave is doing when it causes a memory shift is that it is inducing a vacuum transition. Okay, so what do we mean by the class of shock waves that we want to consider? So far, the analysis that we have written down, there's the memory effect, which is causing a transverse shift in the shear. So here, what we want to do is we want to perform linearized diffeomorphism that gets rid of the memory mode in the transverse direction. And what ends up happening is that you pick up a piece in the longitudinal direction. That is a delta function. And this delta function is precisely what we mean when we say that this is a shockwave metric. Typically, we think of this a shockwave metric as having a delta function singularity. Now, of course, so everything we're going to be talking about today is going to be at the linearized Einstein, linearized gravity level. So now, what we can do is we can look at the Einstein equation again with this metric, and we have this following constraint equation. Now, there's just 2 points I want to point out. The first point is, suppose we turn off the body mass aspect. So this term goes away, and this term goes away. Now you see that in order to turn on the memory mode, N, you need some non-trivial stress energy tensor on the right-hand side. And this makes sense. Typically, when we want to source shock waves, we turn on some matter to source it. But the part that I want to focus on is suppose we don't turn off the body mass aspect. Now we can turn off the matter stress energy tensor, and we can still satisfy this equation. So now we see that the changes in the body mass aspect itself can source these shock waves, and we really do not need the matter at the end of the day. So now what we want to do, I have presented the class of memory metrics and also the class of shockwave metrics. What we want to do now is to derive an on-shell action associated to both of these types of metrics. And the way that we're going to do this, ensuring that the variational principle is well defined. Now, in general, the on-shell action is not invariant under the diffeomorphism. But as we will see, once we add a corner term, we will be able to obtain a gauge invariant action. This was already explained to us by Donnelly and Friedel back in 2016 of how to do this. Now, every time I talk about the variational principle, I have to tell you what boundary conditions that I am imposing. So what we're going to do is we are going to fix the Goldstone mode to be held constant. And what this means is anytime we have a variation, like we have a shift in vacuum, this is due to the memory mode. And so that like we're holding the reference vacuum to be fixed. And this seems like a physically sensible thing to do. Yes?
Thank you. Don't you think this boundary condition is too strong? Because you kill not only the super translation, but also the translation, no?
So strictly speaking, the only thing we really need to fix is the transverse derivatives of this. It is, yes, there are certain, in many regards, this boundary condition is a little bit restrictive. And it is an interesting question as for whether or not we can relax this appropriately to study other classic boundary conditions. But because at the end of the day, we have to choose, in order for this variational derivation to make sense, we have to impose some form of boundary condition. I guess what I want to moving forward is in this restricted context, I'm able to write down on-shell action, but it would be a very interesting question to see how much we can relax this. But in case, for the purpose of this talk, for the purpose of what we want to do, the only thing we need to restrict is that delta of dz square of c is equal to 0.
Only dz squared,
only
not
dz, yeah.
dz square of c. Okay, so
yeah.
You still kill the pure super translation.
Yes, that's right.
Okay, it's not problematic for the construction? Because you said that you need at some point the super translation invariance for your construction to work, if I'm not mistaken.
Well, so because everything we're doing at the memory, the CZZ, it depends only on dz square of c, right?
Yes.
And so the only thing the only thing we need to fix is that this entire piece is constant. But of course, one could ask if there's some like sort of mixed boundary condition or that can be imposed, and that itself could,
I see. Thank you.
Yes. Okay. And finally, we are going to be working to linear ordering, and time permitting, I'm happy to discuss for why there's technical obstructions to move into quadratic orders in N. Okay, so basically, so what we know is we simply just evaluate the variation of the Einstein-Hilbert action and then substitute in what the memory metric is, and you get this big mess. Now, you don't need to worry about most of these terms. The only thing I want to point out is that notice that if you set delta c is equal to 0, this term completely drops out. And furthermore, the first line, it turns out, only gives you contributions that are quadratic in n. Now, if you do that, that means that the only term that shows up is this total variation in c times n. So you can cancel this by adding a boundary term of the following form. Now, you can repeat the exact same story for the Shockwave metric, and now you need to work only a little bit harder because now you want to have these deltas acting on c rather than n, but you can do the standard integration by parts kind of analysis, and you pick up total variation terms, and at the end of the day, you see that you can cancel out all the variations if you add a boundary term of the following form. And notice that, yes, notice that they're exactly the same, save a factor of 2.
But here you have chosen a specific gauge to write the boundary counter term. So what do you guarantee that this choice is diffeomorphism invariant?
So this choice will not be diffeomorphism invariant, as we will see. In fact, because if they were diffeomorphism invariant, then this boundary piece would be precisely the same as this. But as you can see, there's currently a factor of 2, which we have to correct for. And this was the content of a paper by Donnelly and Friedel of how do you correct for this. Yeah. As for how to do it from the start in a diffeomorphism invariant manner, which I agree is the most palatable, currently we do not know how to do it. So this is just a first approach towards trying to write down on-shell action. Thank you. Okay, so as I mentioned, currently there's a factor of 2 difference between the Shockwave and the memory on-shell action. And the reason this is showing up is because in general, the variation of the Einstein-Hilbert action is not diffeomorphism invariant, as was pointed out by this paper by Donnelly and Friedel. But this can be remedied if you add to the Einstein-Hilbert action an additional boundary term of this following form. Okay, so what happens to the on-shell action once you add this piece? For the memory metric, this extra boundary term, it gives you a contribution that is a 1 over 32 pi g Newton times this cross term. But for the Shockwave metric, actually, there's no contribution because the point of the Shockwave metric was that you removed all of the memory mode in the transverse component of the metric. So at the end of the day, the final gauge invariant action on scribe plus is given by this cross term times 1 over 16 pi g Newton. And the last thing that we need to do is impose a matching condition because so far our analysis have been focused on scribe plus, but there's also a contribution from scribe minus. So to do this, we just impose a standard antipodal matching condition on the shear. And what we end up getting is an important factor of 2. And this is a final gauge invariant on-shell action that captures both the Shockwave and the memory metric. So now in the last bit of the talk, I'm just going to demonstrate that the gauge invariant on-shell action that we have derived is in fact a already familiar quantity. It is namely the soft supertranslation charge, the soft effective action, and the Shockwave effective action. And at least to our knowledge, this provides to leading order in the memory mode N a derivation of these effective actions from a first principles analysis. So let's start from the simplest case. So for the soft supertranslation charge, here the supertranslation charge is usually parameterized by a function f times mb. Here we're going to set f is equal to c, the Goldstone mode. Now I can rewrite this as an integral over scribe at the cost of a u derivative on mb, and then I can use a constraint equation. And to linear order in n, what I get is the following form. But now I can just substitute in the memory metric, and then I just do a couple of integration by parts on the celestial sphere. And lo and behold, I get minus 1 over 8 pi g Newton times this. So this is exactly the gauge invariant on-shell action, including all factors of 2s and pi's and so forth. Furthermore, let's see how it's connected to the soft effective action. So the soft effective action, it is originally defined by Kappa and Mitra in 21 to be the action that appears in the path integral once we integrate out all the energetic modes. And the way that they derive this is using effective field theory techniques. They just require that it reproduces infrared factorization as well as the soft graviton theorem. And what is wonderful about this soft effective action is because the soft sector is universal, the Weinberg, which is another way of saying that the Weinberg soft theorem is universal, the soft effective action is universal as well. It's applicable to all sorts of theories. So at the end of the day, it just requires a bunch of translation between the notation given by Kappa and Mitra, where they use slightly different notation for the soft and Goldstone mode. And you just go through the algebra, and at the end of the day, you get precisely the same thing. And I just want to point out that there is an analogous result in QED, where there we were able to not only get the linear term in n, but the quadratic order in n. And I can explain why there we were able to go a little bit further. And one thing we would like to do is try to extend that analysis to gravity as well. Okay, the last piece of information that I want to say is a Shockwave effective action. So this was recently used by Verlinde and Zurich to study these what happens to metric fluctuations in the presence of a Shockwave. And the action is typically written in terms of these variables that corresponds to the position of the Shockwave and the momentum of the Shockwave. Now, it was derived in 23 with Anna and Catherine that there's a way of mapping the Shockwave variables, the momentum and the position, to the soft modes, the memory mode and the Goldstone mode in particular. So now all you need to do is just substitute in what this mapping is, and at the end of the day, you get once again the same answer. And so this is precisely, so at the end of the day, what we see is that all of these quantities that people have been studying in a variety of contexts in infrared sector are in fact the same. So to conclude, as I'm out of time, what we did was we derived a gauge invariant on-shell action for a particular choice of boundary conditions. And one thing that we would like to do is try to understand how physically meaningful those boundary conditions are, or whether or not we can relax them. Now, we would also, the other thing that we showed was that this gauge invariant on-shell action, the reason why it might be interesting is because it is precisely equivalent to 3 different things that have already been studied and quite familiar in the literature, namely the soft supertranslation charge, the soft effective action, and also the shockwave effective action. So this is certainly not the end. There's quite a lot of things that are still we're trying to sort out and understand. One thing I already alluded to is that we want to figure out what the order n square piece is. Another thing that it would be interesting to understand is the implications of the soft supertranslation charge when it is parameterized by a field. Now, normally it's parameterized by a function f, which is a constant on phase space. But if it's parameterized by Goldstone mode, then this is something that is perhaps a little bit less familiar, and we would like to better understand what that object is. So basically, I want to end by saying that indeed, this is not the end, but the beginning, and there's many exciting avenues to explore in the context of both celestial holography and the connections to observables. So thank you very much for your attention.
Thank you. We have a little time for a couple of questions.
Yeah, I guess 3 is the perfect number for advertisement purposes, but maybe to add a fourth one. I was wondering because there were papers like in the 80s by Drey, Toft, and then also another paper by Ferrari, Pendenza, Veneziano, in which I think they were also studying the effective action for shock waves. I think in their case, they had one shock wave and another massless particle, which was not very energetic. So in their case, eventually, in fact, there was also a discrepancy by a factor of 2, if I remember correctly, at some point. And eventually there, they claim it was equal to the iconal phase. So that what Paolo presented this morning. So yeah, I don't know, maybe this is a...
I see. Is it, so out of curiosity, it's not this, what they were saying, I was under the impression it was precisely related to this action that Verlinde wrote down back in 91 because...
But that was in 85.
Yeah.
Rate of paper.
That's true. That's okay.
I don't know, maybe it's worth looking into. Maybe there is an extra bullet point that we added to the story. I don't know.
Yeah. I mean, there's a parallel story that I didn't talk about, which is that the fact that you can do this mapping, this is precisely what you will get is a lot of these commutation relations that Tuff wrote down back in the 80s that relates this shockwave position and momentum, where Tuff sort of argues for in a sense that if you have a commutator between position and momentum, they have to be canonically conjugate. And the way that we see it is that this is precisely the statement corresponding to this to these commutation relations between the soft modes. So I think it is almost certain that they are related. But I'm not as familiar as the fact that they wrote down effective action for it. But maybe
no, I guess the difference is here, as far as I understand, you only have one shockwave, right?
We only have one shot. Yes, we have only one shockwave. But it's a question because the problem with 2 shockwaves is then you get the singularity that shows up when the 2 shockwaves collide, and we don't know what to deal with.
Yeah, in that case, they had one big shockwave, let's say, and another tiny one, which was looked as a probe.
Okay,
yes. In that case, there were, eventually there were delta functions here and there, but there were no delta squared, as far as I remember.
Yes. Yeah.
Can these can you have these affect?
That's a good question. So short answer is I don't know. What in principle what one could do is the way that we derive this, the reason why this is a leading soft is because assume this particular class matrix. Now the subleading soft, we would just need to essentially assume a slightly more general form for this for this shear profile. And ultimately, I do suspect that to get this, so the reason why we can't extend this to the order n squared case is because if we take this profile and NZZ, it has a delta function. And so NZZ squared has delta function squared that we aren't entirely certain how to deal with. So in order to get the n squared, the R divergent piece, I suspect we will need something that will require our to go to the subleading level. And that will basically require us to regularize the step function to something a little bit more smooth. And then once we are able to do that, then we can sort of look at it order by order. Yeah, so this is probably where we will have the modifier analysis to look at the sublinear level.
Okay, I don't see more questions. Anyway, it's time to move on. Thank you a lot, Temple.
Okay. Yeah. Mm-hmm.
Okay, so for the last talk of the day, we are very pleased to have Massimo Porati from NYU, who is going to tell us about Lorentz covariance super translation. Let me read the title because quite long frames for the angular momentum aspect and its flux in finitely radiating systems.
Thank you very much. Thank you for giving me the opportunity of speaking at this conference. It's an important anniversary for me because I spoke here 20 years ago, give or take a few months, at the inaugural conference at GGI. I don't know if any one of you was here or remembered what I talked about. Anyway, it was no-go theorems for massless high-spin particles. So we keep on being in the same vein. Okay, so here is what I want to talk about. I think that the title says it all. So let me just tell you the structure of this talk. I will just review for probably the 15th time today the metric and symmetries of asymptotically flat space and the BMS algebra. I will mention the ambiguity due to supertranslation in the definition of the angular momentum and, in fact, angular momentum aspect, also known as superrotation charges. I will define what is energy, angular momentum, and mass dipole once the angular momentum aspect and the mass aspect is defined. And then I'll give a physical interpretation of the angular momentum aspect, also including a very Gedanken experiment on how to measure that. Since there is so much beauty in Florence and so much elegance, I want to give an ugly resolution of the ambiguity for a change, right? And so let's try to not forget that sometimes ugly is good. And then mention that this ugly resolution has a problem with covariance. I will also point out to which covariance I'm talking about. And then I'll resolve the problem due to covariance and the attempt to make those charges covariant for all the aspect. And then I'll resolve some additional ambiguity that is present when we are not looking at charges, but we are looking at fluxes. And then I'll mention something about the relation with other definition of charges. And then we party, right? So, okay. Okay, so let's start with the definition. So the metric of an asymptotically flat space-time near future null infinity can be written in the Bondi gauge in terms of retarded time, radius, and two angles. In this way, now you have seen it several times, there is a leading term in the metric that, as was pointed out in the previous talk, is just the flat metric. This H is the round metric of the two sphere. And then there are subleading terms. There is a shear term here, right? There is a mass aspect. This M depends on both U and theta. And then there are other terms. Now you may notice that in the du d theta term, the leading term that goes like R in this expression is not new, is fixed in terms of the shear, but at subleading order, you have a new term that appears here, and that's the angular momentum aspect. There is a zoo of definitions of the angular momentum aspect. I'm using one that makes the definition of angular momentum and fluxes easy. Other are present in the literature. Okay, so this metric is invariant, as you know, under Lorentz transformations. They act as conformal isometries of the celestial sphere. So for me, these isometries will be defined by vectors y that obey the conformal killing vector equation. Rotations have d dot y equal to 0, are divergenceless. Besides that, as you know, there are super translations. At leading order in the radius, they shift retarded time by an amount that depends on the angle, and also do things to the angles at subleading order in 1 over r. Now, the key point, of course, is that they transform the shear inhomogeneously. If you change coordinates according to the rules of tensor transformations, right? C goes into this C prime of the new coordinate U prime. That's equal to the old C plus stuff. So this is the additive stuff that makes the shear, gives interesting effects on due to super translations, right? This F does not depend on U, but depends on theta, right? Okay, so that's well known. There are any questions here? I don't think so, right? Okay. So next, the supertranslation charges are defined, we could have defined them in terms of m, but we define them in terms by taking an integral over the celestial sphere of m with the supertranslation parameter f, right? And the good old energy momentum tensor is just given by the first two harmonics of f. I mean, when you substitute to f the scalar and the vector harmonic and you integrate, you get energy and linear momentum. There are also charges associated to Lorentz transformations. They are obtained by integrating the angular momentum aspect on the sphere with one of the conformal killing vectors. For some manipulations that we'll do in the few next slides, it's useful to remember that this y can be written as the gradient of a boost and the dual of the gradient, sorry, the gradient of a scalar, that's a boost, and the dual of the gradient of another scalar, and that's rotations. And both psi and phi are actually vector harmonics, so they obey this equation of the celestial sphere. This is the covariant derivative with respect to the flat metric on the celestial sphere. Okay, so these are the supertranslation charges. These are the Bondi charges. But these are the Bondi charges. They are not conserved, right? The Bondi charges are interesting because they are not conserved. They change when you have radiation. The true conserved charge is the Bondi charge computed at the past or future infinity. Right? And I'll remind you that by proving this, we prove that there are many more charges than these ones that are being conserved. The reason is that we can repeat the expansion that we had at future null infinity. At past null infinity, we just substitute advanced time to retarded time, or we send the radius to minus infinity, as it was explained in the last talk. And then you have a very similar Bondi gauge expansion of the metric near past null infinity, in which the tildes quantities are the ones defined at past null infinity, in which the thetas are identified antipodally in between past and future infinity. Right? Well, with this antipodal identification, the matching conditions that we have for C and especially for N are very simple, are these ones, right? So the angular momentum aspect at the past or future null infinity is equal to the angular momentum aspect at the future of past null infinity if we identified antipodally the charges, and that's actually the conservation of these charges. So all these N's are conserved charges, actually. Now, when we define the total angular momentum aspect flux through future null infinity, instead we are interested not in the conserved charge, but in the difference between the two charges at the future of Sky plus minus the charge at infinity. So we are interested in this difference. That's just to set notations. Right? Okay. So, of course, as we have seen several times today, we can write the fluxes of both angular momentum aspect and mass aspect as bulk integral on Scri+, right? We just use the time and time transverse coordinate component of Einstein's equations. You have seen some here. This little m should be capital M, really. So you have seen this equation a few minutes ago. This is the evolution of the mass aspect. So you see, if you integrate in U, you get that delta M is written as an integral in U. Same thing for the angular momentum aspect, where there are a lot of terms, and some terms are soft, right, are really memory terms, these linear terms, and some are hard here and here, etc. N is the bonding use, as usual. Okay, so if you are interested in writing an equation for if you want to think about these charges as generators of symmetries on a phase space, you want to write them as an integral in I, but this is not what I'm going to do. I just want to define the charges, right, and the fluxes. So there will be nothing Hamiltonian or canonical in this talk. Okay, now, so instead, one thing that I want to say is to point out that actually it's not that difficult to have an experiment, a Gedanken experiment, a fake experiment for us, that measures actually the angular momentum flux. Right? And the reason is that, the reason is that when you take any null ray that moves in the asymptotic metric, well, it moves along a null geodesic. So if you write a light ray that moves at fixed radius in the coordinates theta, right, and you have this equation where lambda is the affine parameter. Right, this is just ds equal to 0. Right, nothing more. P and Q are essentially the terms in the metric. P is the term that multiplies du d theta, and Q is the term that multiplies d theta d theta. So they have these expressions. Now you may appreciate that, as I showed you earlier, in P, the leading term has nothing to do with the angular momentum aspect. It's actually the divergence of the shear. Right? So, okay, that's so, well, when you take a light ray that moves in at fixed radius in a tiny loop, this thing returns after a time that is given here. And it's more, now there is this ugly term and this term that is less ugly. I may have forgotten 1 over r, noblesse oblige. I mean, again, this is a Gedanken experiment, right? And so, now, what is interesting is that instead, if you take the time delay between two paths that move in opposite directions, and you look at the time delay after they go around a tiny circle at fixed radius, you get this expression that depends only on P, is the circuitation of P along the loop. That can be written, of course, as the integral over the area subtended by the loop of the curl of P as a two-dimensional vector. And you may notice that in general, this thing does not tell us anything about the angular momentum aspect, because the dominant term in P is this. So if you are interested in studying actually the flux at finite U, well, you have to work hard, right, to find what is this flux. But we are interested instead of in something simpler, in computing the total flux of angular momentum aspect long before radiation has arrived and long after the radiation has passed. So we are only interested in computing this delta at plus and minus retarded time, plus infinity and minus infinity retarded time, if you want, in a non-radiative region, in a strictly non-radiative region. Now, in a non-radiative region, the great thing is that C becomes actually the double gradient of this of a scalar function. I call it the electric part of the graviton, boundary graviton, whatever. Right? So actually, in this case, when you are interested in computing the flux of the angular momentum aspect in non-radiative regions, so when you wait a long time, a very long time, then you actually compute exactly the curl of n. And this is actually the part that contributes to angular momentum. So if you had the advanced civilization that was mentioned in one of the previous talks, right, and you integrate over the celestial sphere, you would be able to compute the angular momentum. But in any case, you can compute the non-gradient part of the angular momentum aspect even by looking at a tiny section of space-time. Again, this works only if you are computing a difference in between two non-radiative regions. Okay, so at least we know what we are computing, right, and what this n means. I mean, there is a very, I mean, all of this actually is very subdominant in the radius, so how to actually compute this tiny difference in arrival times is another matter. Yes? Oh, this is the time, the difference between the time that it takes light to go clockwise and counterclockwise around a tiny loop at infinity. So I have
Is the light moving on a geodesic?
the light is moving in a circle, yeah, in a null line. It doesn't need to be, well, it could be piecewise a geodesic, but you could have an optical fiber or mirrors that make it move on theta. So the
And on your choice of R coordinate and things like that.
it depends on the R coordinate. So this is, again, the leading term. It also depends on the fact that I am measuring this loop with respect to fixed coordinates, which are not geodesic observers, but the difference between the two at large R is subdominant in 1 over R. So the key point is that here in non-radiative regions, this tiny effect is dominant in 1 over R. So the difference between geodesic probes and coordinate probes is a subdominant effect. Here I am assuming that I can wait long enough that this C has this form and that the deviation from this form is subdominant with respect to possible, is subdominant in 1 over R, right? So this, of course, means that I have to really look at localized gravitational waves. And at least a localized gravitational wave decay in U with some U to some negative power. So it's an independent parameter. If I have all the time in the world, then I can find a region where this is a good approximation and the deviations are smaller than 1 over R. Otherwise, I will, in this formula, as I showed you before, the leading term would be this, right? But this leading term will be 0 up to order U to the minus alpha, where alpha is some positive number. So this is an independent parameter that ideally I can use to control the approximation. Now this, having all the time in the world didn't work well for James Bond, if you have read in Her Majesty's Secret Service, but let's suppose that we can do that. So now in this definition, there is a physical non-uniqueness due to supertranslation. I can actually change this n that I can measure with a supertranslation, and in non-radiative regions, the angular momentum aspect transforms in this way. In non-radiative regions, the mass aspect does not transform. The formula in the radiative region is more complicated. So essentially, if I want to give meaning to this quantity and associate it to an angular momentum aspect, I also have to fix the supertranslation frame. Either have a formula that's supertranslation invariant or fix the supertranslation frame. And I will do it, again, as promised, in an ugly way by fixing the supertranslation frame, not by looking at a formula that is invariant under supertranslations. So there is a natural way to choose this frame. And first of all, for now and for a little while, I will talk about the charge, so n computed at minus infinity. Then I will talk about the flux, the difference between two n's at plus and minus infinity, at u equals plus infinity, minus u at minus infinity. So a natural choice would be to choose a metric that is as round as possible in the past at u equals minus infinity. If I have some shear in a non-radiative region, I can always cancel the shear with a supertranslation, right? Now, notice that my choice would be, where do I compute this? How do I define an angular momentum and an angular momentum aspect? By choosing a frame where C is 0 in the past right, in a non-radiative region. This is done by a supertranslation, but it only fixes the harmonics with angular momentum larger than 1 in this in the electric shear in C. So the S and P waves in C are still undetermined. Yeah. Now here, this actually creates a problem with covariance if we don't treat these two harmonics properly. The formulas for the angular momentum aspect, M, etc., are covariant if we transform the N and M covariantly. So if we really do the coordinate transformations at infinity and see how these quantities transform. In particular, this means that the mass aspect transforms as a conformal primary of SL2C of weight 3/2, and the supertranslation transforms as a conformal primary of weight -1/2, with formulas given here. Right? So these are transformations of primaries. These transformations follow from the asymptotic form of Lorentz transformations of the matrix. So this is what I mean when I talk about covariance. I mean exactly what we think it's covariance. I change coordinates, I see how the fields transform, and that's what I call coordinate transformations. That seems a silly point, but it will come back at the end of the talk. So why don't we choose, we do a gauge choice? Well, a gauge, frame choice, not gauge, frame. Well, let's choose this frame, the frame where the double divergence of C is equal to 0. So this choice is covariant. It's a nice covariant choice, right, that fixes the frame, but instead choosing the, this does not fix the last two harmonics, so the first two harmonics in supertranslations, choosing the S and P wave in the supertranslation and setting them to 0, it's not a covariant choice, because generically, to go to this frame, I need to do a lot of supertranslations. For instance, supertranslation with angular momentum larger than 1. And Lorentz transformations mix those with the scalar and vector harmonics in F. So this is an important point. It's elementary, but important. So let me go through it. The boost of an L=2 harmonic, in particular, contains a non-zero L=1 harmonic, generally speaking. Right? So I cannot choose in all frames F=0 for the first two harmonics, for the S and P waves. Right? If I had to do some transformation with L larger than 2, they creep down, and then they change also the first two harmonics. Okay, so to see this, we parameterize the boost, as we announced earlier, as the divergence of a scalar vector harmonic to base this equation. And then we just use the transformation of F, which looks like this, which looks like that. Now, with a little bit of integration by parts, right, and using the fact that for an L=2 harmonics, the square of F is -6F. This is L times L+1, right? We can just use this formula, use this and a bit of integration by part, and reduce the transformation of F to this expression. So, does this transformation contain an N=1 harmonic? Yes, because when you apply the 2D Laplacian to the product of F times I, and you select the L=1 component, this square is equal to -2, so this object is, this quantity is -1, -1 plus 5 is non-zero, right? So you cannot just by decree set F=0. And you may wonder whether this is a problem because we chose a particular frame using the double divergence of C. Is there any way to take care of this problem? So is there a way of fixing supertranslations, but not fixing translations? When the answer is no, right? We cannot do that. The problem is unavoidable. Because supertranslation invariance plus covariance means that you have translation invariance. So any supertranslation invariant object, like the angular momentum aspect in a given frame, which is also covariant, if we still want covariance, must also be invariant under translations. We cannot avoid that. So, and the proof is very simple. The proof, in fact, is elementary, right? I mean, we use Jacobi identity. S is a super translation. J is a Lorentz transformation. F is any object that transforms exactly like we expect, say, the angular momentum, like an antisymmetric tensor. But this could be any covariant object. And then, well, we can use Jacobi, right? That sets this sum of 1, 2, and 3 equal to 0. And now covariance on an antisymmetric tensor means that the commutator or Poisson bracket, I mean, this could be like braces or brackets indifferently. This commutator is linear in F. This is true for any covariant quantity. For any covariant quantity, if you do a Lorentz transformation of a covariant quantity, you get a linear combination of the same quantity, right? So this is actually applies to more general quantities than just the angular momentum boost, etc. On the other hand, if we want this F to be supertranslation invariant, then the commutator is 0, right? Which means that, okay, this term is 0 by supertranslation invariance. By covariance, this F commuted with J is proportional to F, which commuted with S is 0. So the first two terms are 0. The third term also must be 0. On the other hand, as we saw before, if we take a supertranslation and we do a boost, we get a translation. So this means that in this, we can arrange S and J in such a way that this commutator is just a translation, which means that F must also be invariant under translations. So there is no way to avoid that, right? This F must be an angular momentum or angular momentum flux defined with respect to a particular coordinate system. And then we cannot fix the coordinate system by decreeing that the supertranslation S and P wave components are 0. So we have to find a better way, a more invariant way to define this coordinate system. Okay, so any questions so far? And okay, so, well, why we want a covariant condition, right? So why don't we use this? The Lorentz generator times the total for momentum of my system equal to 0. Right? In the rest frame, where in the rest frame we are working at u equal minus infinity, right? Before the gravitational wave has passed. In the original rest frame, in the initial rest frame, there is no linear momentum. So this condition reduces to Ji0 equal to 0. Zero mass dipole. That, by the way, is a condition that everybody uses doing perturbative calculations and computing scattering amplitudes. You always go to, you choose as origin of your reference frame the center of mass. So this in reality is something that is done, whether, I mean, then sometimes we don't even bother to say it, but this is the condition that we'll impose. It's very natural, right? And again, means that you are choosing the origin of your coordinate system as the center of mass. This seems obvious. What is not obvious maybe is that we are translating this condition of choosing the origin of your coordinates as the center of mass in terms of the boundary data that are defined at Sky Plus. And so that's maybe the only interesting thing. So in other words, the interesting thing maybe is to rewrite this condition or this, right, in terms of boundary metric quantities. And we can do it actually quite easily. So the angular, you can think of the angular momentum as a map from conformal Killing vectors to the real numbers. So J of Y, J is belongs to the dual space of conformal Killing vectors. If you take the dual of the dual, you get back a conformal Killing vector. So with this definition, right, you for each rotation you define a vector Y of J, right? That is the dual of J of Y, and then you take this vector and you impose that when you do a Lorentz transformation with this vector, right, on the mass aspect, in particular on the first two harmonics of the mass aspect, you get 0. So that's the condition written in terms of boundary quantities, right? You take a vector associated to a rotation, and then you use it to rotate or boost the metric, and then you take the first two components equal to 0. Now, this condition actually reduces to what we had before, to ji0 equal to 0 in the initial rest frame, because in the rest frame, there is no linear momentum. So the vector harmonic for the mass aspect is 0. Then you only have a scalar harmonic here for the mass aspect, also known as mass or energy. That's invariant under rotation, so this condition is satisfied trivially for rotations. For boosts, instead, when you take a boost of the form divergence of a scalar function, a scalar vector function, obeying this equation, and you substitute in here in the formula, in our definition, you get that the y times n integrated over the celestial sphere over y is a pure boost is equal to 0, which is nothing but this, right? Written in the language of BMS objects. So this is very concrete. This is a very concrete way of fixing super translations, because now if you take n and you change it by a super translation, which is given here, right? And you compute its integral against a pure boost, against the divergence of a vector harmonic, you can actually do everything very explicitly. You can substitute a given vector harmonic, say y1m, m is the magnetic vector number, angular momentum number, J3, right? And then you get this formula that fixes the 3 space translations very explicitly in terms of the angular momentum aspect, right? In fact, the angular momentum, right? The mass dipole, the initial mass dipole. So you have now we have fixed the vector components of the super translation. Now, if we just look at the angular momentum aspect at minus infinity, that's all we can do. There is actually the scalar component of the super translation never appears in this condition, right? But can we fix it? I mean, is it useful? Does it have any use? Well, actually it does. Well, first of all, though, we have to take into account a little question. You may say, well, actually, you already fixed the double divergence of C to be equal to 0, but now you also have another condition. Is that other condition compatible with the fact that you fixed the higher harmonics of the super translation with L larger than 1 using this? Because you may say, well, actually, let me fix F, the S&P wave for F. Do a Lorentz transformation. Couldn't that instead give me an L equal to 2 that then interferes with this condition? The answer is no, because one good thing of the Lorentz transformations that you can check using the formulas, using the fact that F transforms like a conformal primary of weight minus 1/2, is that by Lorentz transforming the S&P wave of the super translation, you get only a linear combination of S&P waves. So you never get an L larger than 1. So the two conditions are truly are independent and are truly covariant. I mean, you have one covariant condition, double divergence of C equal to 0, another condition that I gave you before, this one, they are, or this, right? They are both covariant and they don't interfere with each other. Now, if you want to define a flux, you also have to say something about the metric at plus infinity after a gravitational wave has passed. Again, I am only talking about a definition of fluxes in non-radiative regions. Even the transformation laws for the angular momentum aspect and the mass aspect during in a radiative region where the bonding use is non-zero are much more complicated than what I gave you here. I mean, are horrible. Okay, so I say that I have to choose what happens in the future after the wave has passed. Well, there are two choices, right? You can say, well, let's fix my frame by taking a metric that is round in the past and then supplement it with the condition that I just gave you for the mass aspect in the past at u equals minus infinity. Now, if we do this choice and we also fix the future frame in this way, generically, after a gravitational wave has passed, it is no longer true that the double divergence of C is equal to 0. There are memory effects that tell you that generically, this quantity at u equal plus infinity is non-zero. There is a gravitational memory, right? Initially, you have CAB equal to 0. After radiation, you have something that's generically non-zero. Well, if you do this choice, so if you measure n with respect to the original metric, original round metric, right? Even in the future, and you compute the difference between angular momentum aspect in the future minus angular momentum flux in the past, angular momentum aspect in the past, then you discover that the angular momentum flux in particular, the most interesting among all those aspects, right, begins at order g cubed, not g squared. And this actually is a choice made, for instance, by Compere, Olivier, and Serraj that define covariant formulas using the boundary graviton at minus infinity, and also done by my collaborators and myself in 22. So you get a flux that begins at order g cubed, right? Because now you are measuring the angular momentum flux in the future with respect to the deformed metric, the one that remained, that has experienced the passage of a gravitational wave. There is another choice. You can choose to measure n at minus infinity using the round metric at minus infinity and this usual story. But then in the future, you can keep this choice just to stay in the same, say that we measure the angular momentum flux with respect to a single rest frame. We don't want to change the rest frame in between initial and final. But instead, we measure the angular momentum aspect at plus infinity in the future round metric frame. So even in the future, we define n plus with respect to the frame where the double divergence is equal to 0. Yeah. So this is a different choice. It's a choice that forgets about memories, right? In which you measure all these angular momentum aspects using always the round metric, both in the future and in the past. If you do that, this choice actually moves the effect of gravitational memories into the angular momentum flux from a radiating source, and this is what gives you an angular momentum flux, among other things, that begins at order g squared. And most literature on gravitational radiation is this, actually. It makes this choice. So this is the choice in which both before and after you use as a reference metric, a round metric.